Okay, so here we have a kind of familiar table. We've seen this chart already from the Energy Information Agency, and I'll just remind you that this is a chart that plots energy consumption in the United States as a source and as a sector, sources being the fuels or the energy inputs, and sectors being what sector of the U.S. economy is consuming the energy. Previously we looked at the whole chart. Now at this point, since we're just talking about generation, what we're really interested in is this dark brown box. It shows that in the United States, 38.4 quadrillion BTUs of electric energy are consumed per annum. That accounts for about 39% of total energy consumption in the United States. These arrows coming out of the brown boxes as they link to the primary energy sources tells us what percentage of that 38.4 quadrillion BTU is provided by each of these primary energy sources. So we look here and we see that a relatively small fraction of total electric power, 1% of electric power, is provided by petroleum. We see that 22% of electric power is provided by natural gas. We see that 43% of electric power is provided by coal. We see that 13% of total electric power in the United States is provided by renewable energy resources. Those resources include hydropower, biomass, geothermal, solar, and wind. And then finally, we see that the remaining 22% of 38.4 quadrillion BTU comes to us from the nuclear electric power sources that we have in the United States. Let's kind of look at it in the opposite direction, though. Of the total petroleum that we consume in the U.S., only 1% of that goes to provide electric power. So we don't rely on petroleum particularly much to produce electricity. The petroleum that is used to produce electricity is typically in small diesel generators, backup generators. We see that 31% of the natural gas that we consume in the United States goes to electric power. The other sources usually being furnaces in homes or in industrial plants, things like that. But 31% of that 26.6 quadrillion BTU that we consume annually of natural gas goes directly, it's being burnt directly in natural gas plants, whether that's a baseload plant or an intermediate natural gas plant. Coal, very different story though. Almost all of the coal that we produce, 91% of the coal consumption in the United States is due to the electric power industry. So they really drive that coal consumption. And that kind of jives with the fact that a little less than half of our total electricity comes directly to us from coal. Renewable energy is an interesting one, and this is actually the one that I wanted to focus on and why we're going in this direction as well, is we produce 9.3 quadrillion BTU of renewable energy, or energy from renewable sources. That only 52% of that, however, is fed into the electric power system. And so there's a little bit of a discrepancy. Well, what else may you do with renewable energy? Energy Information Agency, landfill gas is going to be counted as renewable energy, so you may burn that directly to produce process heat or something like that. So that's accounted for that. But what's really big, what's really driving this number down to 52% is that if your renewable energy electricity production facility is not owned by the electric power industry, it's not counted in this box. So for example, if I am an industrial facility and I have a bunch of solar panels that I'm using to produce energy for my process, that counts in the industrial block, not the electric power block, right? The only way solar panels would count for the electric power block is that if the utility owned them specifically. So this 52% specifically means utility scale renewable energy resources. Finally, we see that really there is no other use in the U.S. currently for nuclear electric power other than to provide electricity for the electric power industry. This ignores a small number of nuclear ships that the United States owns, primarily submarines and aircraft carriers that have nuclear drives on them. Not the topic of this class, but it's kind of interesting to know that that number is not actually 100%. We do have nuclear aircraft carriers and such things. So if we were to look at this again, we would see that this renewable energy, it produces, 13% of total electric power. Well, where does that 13%, how does that stack up amongst the sources that get lumped in here? if we were to break that 13% down into its constituents, it would be 7% hydropower, it would be 1.47% biomass, it would be 0.41% geothermal, it would be 0.23% solar energy, and it would be 4.13% wind. So what that is saying is that if we were going to rank them, renewable energy, 7% of US supply, or roughly a little more than half that number, is being provided by hydropower. So, you know, a lot of people don't consider hydropower a modern energy source because it's been around for a long time, but it is renewable, right? It just requires that rain falls, although you do have to build these dams to harness that. But these renewable energy statistics that the US government puts out, almost always that includes hydropower in that. And hydropower makes 7% of that 13, right? So more than half. Right? Next, we would get wind at 4.13. So from the truly modern renewable energy resources, wind provides by far the bulk of the electricity, the remaining electricity, right? So we've got another 6% to deal with after we account for hydroelectricity, and 4.13% of that comes from wind. Interestingly, the next is biomass. You know, we talk a lot about solar, but there aren't a lot of utility-sized solar plants out there. And the next one is actually the burning of biomass. So, you know, switch grasses and wood and things like that produce 1.47% of our electricity. Then we have geothermal plants. And finally, rounding out the bottom of the utility industry is solar. Now that doesn't mean if we looked at all electricity that solar would actually be at the bottom, but most of that solar is going to get funneled directly into residential and commercial, right? 11% of solar actually goes into residential, or 11% of renewable goes into residential and commercial. And EIA doesn't tell you what that fraction is in solar. It's a little hard to track. So, let's look at actual totals, though. So instead of looking at it in terms of percentages, let's look at bulk electricity production. So here I have a couple charts to kind of quantify this. And we're going to express them in terms of megawatt hours instead of the quad. And it results in this this table right here. We see that, and this is generation in the United States for 2011 in thousands of megawatt hours. So coal produced 1,514,043 megawatt hours. So multiply that by 1,000 and you get the total number of megawatt hours. So that's 1,514,043 times 10 to the third times 10 to the sixth, so times 10 to the ninth total. We see that the next one behind that is natural gas at 1,225,894 megawatt hours. We then come down to, we've got nuclear, 769,331 megawatt hours, followed then by conventional hydro at 240,000 megawatt hours. We then come underneath with wind, 140,822 megawatt hours. So a good amount of power, although nothing compared to coal, really, at all. All right. Our next is interestingly going to be wood. So we get more electricity from wood than we do from solar energy currently, 37,799 megawatt hours. Then in descending order, we see that we're at petroleum at 23,190 megawatt hours. We then will come to other biofuels. So these are switchgrasses, sawgrasses, you know, algae sources, things like that at 19,823 megawatt hours. We'll then have other gas. Other gas includes landfill gas, sorry. Then we get other sources, and then finally we find out that actually solar contributes a relatively small fraction, even in context, or particularly in context of the net generation. And then finally, I just think it's interesting, what if we were to just go around the United States and count up the number of power plants in the US and then sort them according to their primary energy source? We'll have the following table here. We see that there are 557 coal plants out there, There are 1,129 plants burning petroleum, even though it makes a relatively small fraction of the total megawatt hours. We have, by a large margin compared to coal, natural gas. There are tons of these plants, 1,714. Other gas plants, there are 44. There are 66 nuclear plants in the United States. There are 1,426 nuclear plants. If we combine all the other renewables up together, we get about 2,000. Hydro storage is a little bit different than hydro. It's hydro plants that have the ability to pump water back uphill. There are 41 of those, and then there are 64 other types of plants. These are plants, I would like to stress. These are count of the U.S. power plants by predominant energy source, not the number of generators. So a single plant may contain multiple generators. This just counts the number of plants to kind of give you an idea of what the spread of these electric generators across the U.S. is. So also of interest is what's going to happen in the future, and this is a diagram or a prediction from the Energy Information Administration, and this is kind of a branch of the U.S. federal government that deals with energy usage, but they also make predictions of where our electricity generation sources are going to come from by fuel type in the future. And so this shows a historical data how electricity consumption has gone up in terms of total energy consumption. We can see that total energy consumption for the United States has just been trending up since 1990, although it's not all that much growth. It's about 1 to 3% per year is about what that equates to. But this line at 2012 is when this graph was made, and so this is all historical data, and then this is predictions based on fuel prices, based on availability, based on existing contracts, based on announcements from industry and things like this. And so what we see here is that this prediction that they've done shows a 5% increase in natural gas consumption in 2040 as compared to the base case in 2012. We see a 4% increase in renewables as compared to the base case, a 3% decrease in nuclear, and a 5% decrease in coal. And one thing that some students do get confused at is they say, oh, we're actually going to use less nuclear power. And remember, these are percentages, so you could consume more nuclear power, but it would provide a smaller fraction of the total. Right? If the pie gets bigger, even if the slices get bigger, they might be smaller fractions of the total. So these just say fractions of total, right? 35% of total will come from natural gas. Well, notice the total is much more than it was currently. So that 35%, well, clearly that 35% is going to be bigger than 30, but let's go to nuclear. We see currently nuclear provides roughly 19% of electric power in 2012. It drops to 16%, but that's 16% of 5.2 trillion. I'm not sure what that. 5.2 trillion kilowatt hours, so that's 16% of 5.2 trillion, where that's 19% of 4.1 trillion or something. So despite the fact that the fractional percentage went down, the total usage of nuclear power may actually increase. When electric utilities, they've got all these different power sources to choose from, when they're selecting amongst these available methods of generating electricity, they have to make choices regarding the energy source and fuel type, the type of generation system, the unit and the plant ratings, or how big to make them, and then also how big to make them in terms of electricity output generation, and then also the plant size in terms of a physical footprint of the plant. These decisions are extremely complicated and a little bit outside of the scope of an introductory course, but they're typically made based upon interrelated technical, economic, and environmental factors. And I've got a table here that I just wanted to go through real quickly to show you what some of these factors are on why electricity companies will choose to generate from one source versus the other. So again, I've just indicated the 4 primary criteria: energy source or fuel, generation system type, unit and plant rating, and finally plant size. So those are the 4 criteria. Energy source or fuel, the things that they have to select between are fossil fuels, nuclear, hydroelectricity, geothermal, and other renewables. So, you might, well, why would you select amongst those? Well, some of them have obvious constraints. If I'm not near any place that I can build a dam, hydroelectricity needs to be crossed off the list. Other ones are less obvious. Maybe there are local laws that prohibit nuclear. That has to be crossed off. What about fossil fuels? Can't you build a fossil fuel plant anywhere? Well, remember, you actually have to get the fuel to the fossil fuel plants, right? There has to be shipping and receiving to be able to get the coal and the natural gas there, whether that's a river system with barges or whether that's a pipeline system for natural gas. Also, as we'll see when we look at the technical requirements of these plants, fossil fuel plants need a vast amount of water, so they typically also have to be located by large bodies of water. So you'll be restricted based on the fuel availability and then also the natural resource availability for the cooling there for common fossil fuels. Other things play in, other considerations play into renewables, such as the availability of the sun, wind speeds, things of that nature. Next, we'll look generation system type. So there's a bunch of different types. So we look first at steam cycle. Do we burn natural gas in a steam cycle plant, or do we use it in a combustion turbine plant? Hydroelectric systems are going to have their own turbine types. We've got combined cycle, which means combine the steam and the gas turbine together in one plant type. We then have internal combustion engines, very similar to what's in a diesel truck. And then we've got other advanced technologies or non-conventional sources. And what is going to influence these? Or what fuel do you have available to you? How big are you going to produce the plant, or how big is the plant going to be? So some technologies are capable of producing more electricity than others. What are the efficiencies of these types of generation technologies? Who's making them currently? Are they even available for you? Then we will go on to unit and plant rating. So the questions here are that we need to ask are, is the plant that I'm going to build, it needs to be capable of serving the maximum electrical load and provide some reserve for reliability and future load growth consideration. This introduced a term here, spinning reserve. What spinning reserve is it's generation that's up online, ready to go. The boilers are hot. They're ready to produce electricity. They're just not being connected to the grid so that if there is a need for more electricity instantaneously, they're ready to go. They don't have to heat up. They don't have to do any additional work. You can call on them immediately. That's called spinning reserve. And the idea there is that the generator is spinning. It's just not connected to the system. Now, so this is, if you're making a large capital investment, you probably want to plan for the future. But you might not be so concerned with that. So maybe you only need to provide maximum electric load. You don't need any of this reserve, right? So then you could go with a smaller plant rating. Well, maybe the plant by itself doesn't actually need to meet the max load. Maybe you can buy electricity from your neighbors, but you want to reduce the costs of that a little bit, so you produce a smaller plant, you produce a little bit of electricity, and then buy some others. So you might select a plant that's just capable of serving most of the expected load, right? And then there's a lot of restrictions on that all these relate to in terms of siting. Do you want to put it near the electrical load? Do you have availability of that fuel source? Do you have that availability of that water source? Clearly, you need to connect a power plant to the grid. So is there an existing transmission corridor that can handle the amount of power that you're going to be putting out there? We have to have the appropriate wires already out there. And if you decide to locate a plant remotely, well, now you have to build a new transmission corridor, which can add a substantial cost. Actually, locating plants near existing electrical transmission systems is commonly cited as the most difficult part of producing a power plant in current times. The regulatory situation in the United States has made it almost impossible to site new transmission lines. So this is a really, really important one when you're choosing the generation type. Is there existing transportation in the system? Can you co-locate it with another generator? Might save you some costs there. So, none of these, the point is none of these operate independently, and so when electric utilities are evaluating these, it's not always just a carbon question. It's not always just a cost question. It's not always just a not in my backyard question. It's this interrelated matrix of different things that affect which power source that you're going to choose. Each combination of energy source and power generating system is going to have its own technical, economic, and environmental advantages and disadvantages that are unique to that combination. Individualities of a particular situation can or will always affect the comparison of various systems. But what I've tried to provide to you here are some typical values for different combinations of plants. So we start on the far column here, and that's energy sources by fuel and system type. So we've got a coal-fired steam cycle, we've got an oil-fired steam cycle, we've got a natural gas-fired steam cycle, we've got a nuclear, we've got a oil-fired combustion engine, a natural gas-fired combustion engine, oil-fired combined cycle, natural gas combined cycle, hydroelectric, and then geothermal steam. So this leaves out some of the more common renewables, but of the conventional sources, it really touches them. And then you can kind of go through this matrix on your own. It compares how expensive is the fuel, how efficient is the system at converting the energy stored in the fuel into electrical energy, what are the capital costs to actually build it in terms of dollars per kilowatt hour, what are the O&M costs, that means how much does it cost to actually run the plant, can I build it large? If I need to produce a lot of power, is this technology suitable for that? Some of these are very suitable for large powers and others are not. Following that, we've got system reliability and availability. What that means is availability is, does the plant have to be taken offline very often for things like repairing the generator, turbine blades, things like that. Then we've got system complexity. How smart do my engineers have to be to build, operate, and fix this thing? Some of them are very easy and simple, and some of them are extremely complex. The fuel that it runs on, is it easy to procure? Do I need large quantities of water for operation of the plant? And then what are the major environmental ramifications of those? So, some plants may win in fuel cost, but then produce large negative environmental consequences. And it's not a straightforward answer of this is better than this. We can't say that, this doesn't include renewables, but we can't say that solar is better than coal. We can't say that hydroelectricity is better than coal. They all have factors that are individual to them that contribute to why we would choose to use those in our generation mixture. And this table really does provide a good overview of what those all are. So please kind of pause the video now, take 10 minutes and read through this to familiarize yourself with the relative advantages and disadvantages of each of these kind of more conventional energy types. Once you've done that, we'll discuss more. Let's say we would compare coal and nuclear energy using this table. We see that nuclear energy has a much lower fuel cost, but higher capital costs. So if we were to look at nuclear energy, it's marked as low in fuel cost, whereas coal-fired, which is really only used in a steam cycle, is marked as intermediate. So it costs us less to get the coal or the uranium that's required for nuclear than it is per kilowatt hour for the coal-fired steam cycle. But then if we move over to the capital costs, we see that the highest is for nuclear. Capital costs are extremely high for nuclear, although capital costs for coal-fired are extremely high. Both of those are very large plants, by the way, so capital costs tend to be high just because they're very big. The economic decision is then based to a large extent on the expected, what we call capacity factor, which we discussed in Module 3, which is the full load hours of operation per year for a unit. So, we look at the capacity factor of the system, we can then use that information to decide, which of these units that we're going to select, and we'll show those calculations here in a little bit. And then I guess if we're going to kind of continue our coal-fired versus nuclear, we look at the major environmental impacts of coal, and we see that it's particulates, SO2, nitrogen oxides in the stack. If it's got any sort of carbon sequestration technologies, we've got to dispose of those scrubbers, the sludge, and then also the combustion of coal produces fly ash that has to be disposed of, so it has solid waste that's produced. Where you get a nuclear, well, there's safety. There is a potential that the nuclear plant could go into thermal meltdown, and that has happened in the past, not often, but Chernobyl and 3 Mile Island. And then finally, the major disadvantage of the nuclear is that it does produce nuclear waste. So then we have to include unit rating and siting. We have to evaluate those when we're looking at the choice of plant. The range of unit ratings are commercially available will be different for each of these generation types. We see the capacity ratings, for capacity ratings above 100 megawatts, for example, combustion turbines, diesel, and geothermal could not be used. Companies just don't make combustion turbines, diesel, and geothermal above 100 megawatt units, right? The plant site is going to affect the choice of fuel that we use, and therefore the power generation system, and also the rating of the plant. Both fossil fuel and nuclear plants require up to a million gallons per minute of cooling water for a 1,000 megawatt unit, whereas a gas turbine actually doesn't require any cooling water. A 1,000 megawatt coal unit will consume approximately 3 million tons of coal annually, where a similar sized nuclear reactor would only consume 36.2 tons of enriched uranium dioxide. Therefore, the coal plants have to typically have a large storage facility associated with them, and they have to have this additional requirement of disposal of large quantities of ash and scrubber sludge. So natural gas units in contrast require no solid waste disposal. The location and physical characteristics of the available plant sites, such as proximity to water, proximity to fuel, or fuel transportation, these can have a significant impact on the choice of fuel and power plant type. So we've looked at this kind of almost socioeconomic, techno-economic, I guess is a better term. We've kind of looked at this techno-economic environmental matrix of what influences why different utilities would select different generation resources. But there are some operating characteristics which also have to be considered when choosing a generation technology. We have the ramp rate, or sometimes called ramp time, which is how quickly the plant can increase or decrease power output. This is measured in typically in megawatts per hour, or in percent capacity per unit time. Generators just can't be instantaneously asked to produce power. They do have to slowly, or in some cases not so slowly, but typically slowly ramp up or ramp down their capacity, and how fast they can change is called the ramp rate. There's the ramp time, which is the amount of time it takes from the moment a generator is turned on to the moment it can start providing energy to the grid at its lower operating limit. There is what's called the capacity of a system, the maximum amount of power a plant can generate measured in megawatts. We then have what's called the lower operating limit, which is the minimum amount of power a plant can generate once it's turned on in megawatts. So there are some lower boundaries. We have what's called the minimum runtime, which is the shortest amount of time a plant can operate once it's turned on, and this is typically measured in hours, right? So we can't turn it on and turn it off immediately. Of these, the minimum runtime and the ramp times determine really how flexible the generation source is, and these can vary greatly amongst types of plants and are a function of regulations, types of fuel, and technology. Generally speaking, we say that plants that are less flexible meaning that they have a longer minimum runtime and slower ramp times, will serve as base load energy, while plants that are more flexible, meaning that they have shorter minimum run times and quicker ramp times, these are typically better suited to fill peak demand. The table that I have put up here shows approximate, kind of in an order of magnitude comparison, minimum run times and ramp times for some of the more common generation technologies. It's important to realize that in some cases these are kind of soft constraints. It is possible, for example, to run a nuclear plant for 5 hours and then shut it down. However, doing this imposes large costs in the form of wear and tear on the plant's components, so it's not recommended. So it's not that the plant physically can't be run for that short of amount of time. It's that you would damage it if you turned it off. So in an emergency situation, could this happen? Yes, I suppose you could run it below its minimum runtime, but it has a large operational cost associated with it. So here if we want to just quickly summarize the ramp times and minimum run times of the technologies, we've got a simple cycle combustion turbine. So these are typically small diesel generators or small natural gas generators. Depending on the size, they can ramp up in minutes or hours, and you can turn them on almost immediately. Combined cycle combustion turbine. This is almost exclusively a natural gas technology that has both a combustion turbine and a steam turbine. It will take hours to get up to temperature, and it has to run for usually multiple days for large plants. So you can't bring it up to generation and then just let it run for a couple hours. Nuclear ramp time is of the largest order of magnitude in terms of days, and sometimes you have to run these things for months at a time. Wind turbines, minutes, and you can turn it off immediately. And then hydroelectricity, minutes, and you can turn it off immediately. There are some real distinct operational advantages of hydroelectricity because of this ramp time and min run time that we'll talk about in later lectures. I've then taken this data and I've kind of plotted it in a relative comparison of operating costs and operational flexibilities for the different power plant technologies. I've excluded most renewables from this analysis since operational flexibility is partially dependent on the prevailing weather conditions such as solar irradiance and wind speed and wind direction and things like that. So we then get this kind of operational flexibility. I'm plotting the zero intercept as the less operational flexibility, and as I move along the positive x-axis, that's more flexible. And then operating costs, I've got extremely low operating costs and extremely high operating costs here on a per kilowatt hour basis. So coal and nuclear, they're not very flexible, but they're extremely low cost. Hydroelectricity has the advantage of being extremely flexible and extremely low cost. As we move into smaller coal units, the smaller the unit, the more flexible it gets, but the more expensive per kilowatt hour it becomes. And we have combined cycle gas turbines kind of following in that same. Although this dot has kind of been trending this way in recent times. Finally, the simple cycle ones, the ones that have really the most flexibility, those tend to be on a kilowatt hour basis, the most expensive for us to use.